Need city students, you can drop that in the chat too. Would like to recognize you. I can see Emmanuel. So, good morning, everyone. We'll start by 11:05 so we can have more people. Oh, Kiki is from Lead City. Welcome, Kiki. Thank you for joining. Welcome, Taiwo. Oh, yeah, Mrs. from Lead City too. Thank you for joining. Razak is from Lupa from Abuja. It's nice to have you here.
Good morning, everyone. Please, I just want to confirm. Can you hear me?
Yes, I can.
Okay.
So, 11:05 already. Hold on. So I'll introduce you, then you would just start. Okay, good morning, everyone. It's 11:05 already. So we are about to start. My name is Ianoluwa Shomi, and I work as the program manager at Techlytics Institute of Technology and Innovation, and we are all about artificial intelligence, data, and automation. And that is one of the reasons why we organize this masterclass, so that people who are getting into AI or just curious about it can learn. Everyone can learn. So today we have with us Emmanuel Adegbite. But before I introduce him, I want us to rate ourselves on a scale of 1 to 10. Your knowledge on artificial intelligence. So we can just put that in the chat box. You can just rate yourself 1, 2, 3, 4, 5. Your knowledge on artificial intelligence. Okay, Olakunle says 4. And you're a boss then. But that's good. That's a good one. I need more people to type in the chat box. So the question is for us to rate ourselves on a scale of 1 to 10. Your knowledge on artificial intelligence. Can we hear me? So Malala says 2.5. That's a good one, and I hope that after today you'll be able to scale up to 5. So let's introduce our speaker. I made a mistake earlier on. I said Emmanuel instead of Heritage. So our tutor for today is Heritage Adegbite. And Heritage is an embedded system engineer. It's focused on computing and intelligent hardware design. He has a background in electrical and electronics engineering, and he's an expertise in microcontrollers, real-time systems, and edge AI. So just know that you're in safe hands, and I want this class to be very interactive. When there'll be a time for question and answers, but if you can't wait till then, you can drop your questions in the chat box so that you'll be able to attend to those questions as it's teaching. It's going to be very, very practical. So let's use the clapping emojis as we welcome Heritage. Heritage, over to you.
Good morning. Can you hear me?
Yes, I can.
Okay. You can also see my screen, right?
Yes.
Okay. I wasn't sure that. I'm grateful to be here. I'm grateful for the organizers for giving me this privilege to teach you guys and impact. It's one of my passions, many passions, to impact knowledge. And we'll just be looking at computer vision this morning. There are certain things I'll explain the fundamentals. Then we would also have a live coding class. So we would actually build the computer vision model. So it's not just going to be all theory. It's going to be also theory and practical. That's how we are going to go about it. So when we think of computer vision, basically it's okay. Let me just look at my slides. Introduction to computer vision. But I'll be using the slides. I'll be also speaking from top of my head. When we're talking about computer vision, we're talking about training a machine to detect images or objects. So a good example is this. You have your phone. Your phone has face unlock. So if you're using a phone, probably you have biometrics, either your face or your thumbprint or your fingerprint rather. So your face uses that. Sorry, your phone uses that. That's one example. Second example is when you look at modern self-driving cars. So when you look at like self-driving cars, they either make use of a camera or a LiDAR sensor. When you look at also sensing, when you look at satellites, looking down again, they make use of computer vision. So computer vision is this: you have a machine, a computer, you are teaching it to learn how to detect objects or images. That's just in summary, computer vision. Now it's easier said than.
Can you hold on, please? So, Bolo mentioned that there is no sound. I want to confirm that everyone else can hear what you're saying because I can. So, can everyone hear? You can just type or like the mic to confirm or a thumbs up before we move on. Can everyone hear sound? Let's see. Okay, yes. Okay, so if you can't, that means you'll have to like log out and log in again. All right, Eric, you can continue.
All right. So it's easier said than done. Well, this morning or today we'll just be building a simple model. But before that, I'm just going to give us some few introductions. So when we look at a picture or an image, everybody knows what a picture is or an image is. Basically, is this: when we're in, I think these are university students, so I can reference some secondary school topics I need to explain. When we're in secondary school, if you did, let's say, sciences, you were taught that the building or the basic block of every matter is an atom. So an atom, when you combine so many atoms together, you get maybe a molecule. When you combine a molecule together, you get a compound. When you combine compounds together, you get maybe like a substance. Generally speaking, that's it. And that's the same thing for images. So images, the building block for it is known as a pixel. So everybody has heard of a pixel before. So you see something like let's say 1920 by 1080. So it's basically talking about resolution. And I want to be sure you can all see my screen. So let's just go to images. So I'll be showing you this in real time. So let's look at this for example. So this is a picture or an image of a cat. But if you zoom in, you tend to see different things. So now you can see red, you can see blue, you can see green, you can see black, you can see white, you can see multiple colors. So that when they add up together, they form a picture of a cat. Let me look for example again. Okay, so this is a bee, for example. We know it's a bee. But when you zoom in, what do you see? You see yellow, you see black, you see white. And so basically, that's how just all images are. Images are when you combine so many pixels together, you get an image. It's really okay. Another example again is this: a picture of a cat. When you zoom in, you see it's not really yellowish. It's more of orange. You see orange. You see black. You see white. You see a white background. So basically, those are what pixels are. Pixels are the building block of every image, and every pixel consists of 3 colors. Or in computers, we make use of 3 colors. We make use of red, green, and blue. So let me show you what I'm talking about. Again, like I said, I prepared for this class, but I also want you to see me do these things live. So let me show you what I'm talking about. Let me say RGB color picker, for example. So every image or every pixel consists of 3 colors: red, green, and blue. So that when you combine these 3 colors in different intensity, you can get any color. So I hope you guys, if you don't understand anything I've said, you can always just feel free to draw me back in the chat. So I'll give you an example now. You can see my screen. So this indicates red, green, and blue. So the first 66 is for red, the green is 135, the blue is 245. Now it's usually in from 0 to 255. So the maximum is 255. So now let's make this 0. 0 is the least. Let's make this 0. 0 is this. So now the red is 0, the green is 0, the blue is, let's say, 255. 255, that's the maximum. Now we see that it's a blue. So we know that red is 0, green is 0, blue is 255. But now if we add green and blue, usually we get something that is cyan or teal. So let me say, so now we've gotten something cyan or teal. So red is 0, green is 255, blue is 255. So we get cyan. Now if we add red, green, and blue, we get white. So if I just add another 255, what will I get? I'll get white. And basically, this is just how colors work or images work. It's a combination of red, green, and blue. So that when you combine them at different intensity, you get any color. So now let me make blue 0. If you combine red and green, you get yellow. That's what we got. If I make this 0, what do we get? We get red is 0, green is 255, blue is 0. We get green. So I'm just trying to make you understand that every pixel is made up of red, green, and blue, generally speaking. Now there's something known as gray images or grayscale images. So when you look at a picture on your phone, these are just basically how pixels are made up of. And pixel is just a short form. The full word is picture element. And when we look at grayscale images, now, before the invention of colored TV, we had black and white TVs. And that's basically what grayscale images are. Grayscale images are just black and white TV and black and white pictures. So let me show you an example. Grayscale images. Okay, let's go to an image here. So let's look at this, for example. So this is a grayscale image. And it's just a combination of black and white of different intensity. And grayscale images, they make use of pixels too. But when they make use of pixels, the way they work is different from the one I've explained prior to before. How these ones work is that they make use of just black and white. And the black and white have different intensity. So this, if something is not too black and not too white, it's going to be, let's say, ash or grayish. And basically, this is how it works. So, example now, when you look at these dog's fur, you see that is more black than let's say this tree side. Or when you look at this region, you can see that it's dark compared to this place where it is white. So we've seen how pictures work or images work. That is made up of pixels. Let me just recap. Pixels are the building blocks of images, and pixels consist of red, green, and blue, such that if you combine them at different intensities, you can get any color. So let me give an example. This is also a color picker. So again, like I said, this is teal or cyan. Let's go towards this is roughly about purple. So if you combine red and blue, you get purple magenta-ish color. So let's go to, where is lemon green? This should be the area of lemon green ish. So this is roughly about lemon green. So if you combine any color, you can get, if you combine red, green, and blue, rather, you can get any color. All right. Then I explained grayscale images also. That grayscale images are pixels, but they are not made up of red, green, or blue. Rather, they're made up of black and white. So I want us to reply in the chat if we understand to this point. Just give a reaction, maybe a thumbs up reaction if we understand to this point. Hello? Am I still audible? Can you still hear me? Okay, okay. Daniel responded. Okay, yes, we got a thumbs up. So I'll just go for that. So now the way pixels work is this, and let me show this on my the way, can you still see the screen? The way pixels work. I'm sorry, it turned white. Let me. The way it works is this. You have three colors. Let me just recap. You have three colors. I'm sorry that, listen. So this is an image. Let me give you an example. Let me make this yellow. Let me just go to you. This is an image. Okay. Let me just make it this background. Yeah. So this is an image. Let's say it's an image of a boy. For example, this is an image. Don't mind my drawing. Now, I said that a pixel, when you combine so many pixels, you get an image. So an image is just a combination of several pixels. So now let's try and break it down. Let's say these are the pixels, for example. The horizontal and vertical lines I'm about to draw are the pixels. Okay, so this is how many rows? 1, 2, 3, 4, 5, 6, 7. This is 7 rows. So this is 7. How many columns? 1, 2, 3, 4, 5 by 5. Now we're entering the realm of mathematics. Now, this is a 7 row by 5. So this is a 7 by 5 image. And I said that each pixel consists of 3 colors, red, green, and blue. So we're going to add the third color. So in secondary school, we did something called matrices, and this is basically what this is. So this is a 3 by 3. Sorry, this is a 3-dimensional matrix. So again, 7 rows, 5 columns, and this 3 is either called depth or channel. So channel in the sense that it has red channel, green channel, and blue channel. Now, these are known as tensors. The word tensors, T-E-N-S-O-R-S. S-O-R-S. They're known as tensors. So when you are dealing with images are just combination of several tensors. So that if we can get an image from it being visual to it being numeric, so if we can get the numbers, we can play around with the numbers and we can make use of computer vision. That's what I'll start with. So I remember I told you earlier on that the minimum is 0 of any color and the maximum is 255. 255. So if I can get the numbers for each color, and I can play around it, I can make use of computer vision. And that's basically just what computer vision is. You get the pixels, you get the numbers, you compute it, you play around with it, and you're able to figure out something. Okay. So when dealing with tensors, we're in the realm of tensors now. Let me erase this. Okay. When dealing with tensors, there are types of tensors, or they're just, number one is that there is a scalar. So scalars are just, if I write number 13 down, for example, 13 is just a scalar. It doesn't have any, so a scalar, we know it has magnitude but no direction. So that's basically what 13 is. So if I just write number 13 down, for example, 13 is a scalar. But if I write, for example, let's say 20 in a bracket like this. Now we are getting to 1D tensors. So this is a 1D tensor. Or let me say, comma, let me add number 2 inside. This is still a 1D tensor. So when we talk about 1D, we're talking about it either having just a row or having a column. So when you look at, let's say, 20, 2 or 20, 3, look at this, 20, 3. We can see that it only has column but has no row. That's what it just has. It just has columns but no row. So it's a 1D tensor. But now, if it has both columns and row, so now if I make a general tensor and I say 20, 3, let's say 5, 6. Now, this is a 2D tensor because it is 2 rows and 2 columns. So such that if you're going to write it, it's going to be 23, 5, 6. This is basically what it is. So it's a 2x2 matrix. Again, so tensors could be matrices. That's just it. So let me just erase everything. Then the third one is 3x3 matrices. And that was what I explained to you earlier. And I want us to visualize it as this. You have a 2x2 matrix. So let's say you have 1, 2, 3, 4. This is a 2x2 matrix. So it's a 2D tensor. Now, imagine you have several of these. So in the next one, you have 5, 6, 7, 8. The next one, you have 9, 10, 11, and 12. Now, these 5, 6, 7, 8, 9, 10, 11, 12, they are stacked so that it becomes a 3D. So we know what 2D and 3D is. So if I just draw a rectangle, this is a 2D, that's length and breadth. But if I begin to give it depth, it's a 3D. So this is a cube. So now, just imagine this 5, 6, 7, 8 is laid up at the back of it, such that it becomes its depth. So it is 1, 2, 3, 4. Then it has a depth. And that depth is 5, 6, 7, 8, 9, 10, 11, 12. So before I go further, I want to just make sure everybody understands what I've said to this point. So if you understand what I've said to this point, please just give a thumbs up reaction. Hello, can you guys still hear me? If you understand what I've said, can you please give a thumbs up reaction? All right, if you want me to go over it again, can you just indicate in the chat? So if you want me to go over it again, you can indicate in the chat. All right, so I'll just move on then. So, okay, someone said I should go over, please. All right, let me just go over again. So we are dealing with tensors, and we should imagine them as matrices because that's what they are. It's just a matrix. And I started off with this. If I just write a random number, let's say I write number 16 down. Now 16 is a scalar. 16 is just a scalar. It's just a number. It doesn't mean anything. 16 what? 16 boys, 16 girls, 16 laptops, 16 students, 16 what? So it just has a magnitude, but it does not have any direction. It doesn't reference anything, number 16. But now, when we begin to move into tensors, we're talking about something that has a point, a direction. So a 1D is just known as a vector. So we know vectors, they have direction. So if I write something like, let's say 26, 3 inside a bracket. Now, this is a vector. So we know vectors, they have magnitude and they have direction. And scalars just have magnitude, they don't have direction. Now, if I put 26,3, it begins to reference something. And we know that this is just columns. So rows are vertical and columns are horizontal. Now, this has no vertical, all it just has horizontal. So it doesn't have any row and it just has 2 columns. So it has 1, 2. So this is a tensor of 2 columns. Now, if I do something like 26 and 3, 26 and 3. Now, we just know that it has rows. So it's a tensor of 2 rows. So do we understand that? That we see the rows here. We see that it doesn't have columns. There's no horizontal. It's just a row. So this is 26 by 3. This is just a 2-row vector. And 26, 3 here, this is just a 2-column vector. That's that. Now, when we are talking about 2D, we're talking about matrices. And when we talk about matrices, these are matrices. So if I write 1, 2, 3, and 4, this is a matrix. This is a matrix. And I said that when matrices are stacked up so that they have depth. So this is, and I give an example of a rectangle. This is a rectangle. Now, if a rectangle had a depth, it would form a cube. So this is a cube. Okay, someone has a question. Someone raised up their hand. Can you please type your question in the chat? If a rectangle had a depth, it would be a cube. And so 3D matrices are this. They are 2D matrices that have depth. So behind this 1, 2, 3, 4 is another matrix. At the back of it is another matrix. At the back of this 3 is another matrix. At the back of this 4 is another matrix. So that when matrices have depth, the question in the chat. If a rectangle had a depth, it's a cube. When matrices have depth, they are known as 3D tensors. And I can just give you so much theory, but let me show you an example. Let me go to Google Colab. Okay. So this is, we'll be using Google Colab for today's lesson. And let me start with the first example. Okay. So the first thing we'll do is this. We are working with TensorFlow. We're going to import TensorFlow and we're going to name it TF. So import TensorFlow as TF. TensorFlow is a Python library. So TensorFlow is a Python library that was developed by Google. So now we're going to say X is equal to TF constant 3. So it's just basically saying X is equal to 3. That's basically what we are saying. And Y constant of 4. So Y is equal to 4. Now when you do 3 plus 4, what do you get? When you run it. Oh, sorry, I need to connect to your runtime. I'm trying runtime type. Okay, let's use this. It's not use so much computing. No, let me reload this. Okay, it's already connected. If I reload it, it should still be connected. So let me connect to your runtime. Sorry for the delay. Okay, it's connected now. And let me just reload this. Oh, okay. Let me just reload this. So we get 7. We get 7 as the answer. Now we see that we don't get any shape. Mind you, remember, because I told you that it's a scalar. I told you that number like 13 is a scalar. Number 4 is a scalar because it has no direction. So it doesn't have any shape. The shape is just blank. Then the type is an integer. So when you see int, it means integer. Then 32, that is the bit size. So it's an int 32 bits. That's a 4 byte. So let's make this one, let's say 6. So we know 6 plus 4 is 10. We should get 10. So basically, the answer is 10. It doesn't have any shape. And again, it's still an integer of 32. Let's go to the next one. Now, like I was saying, let's say we make it Let's say we make it a 1D 1D tensor. Sorry. Let's say we make it a 1D tensor. So we say that B is now, again, we give it a bracket 1, 2, 3. Let us run this. Now let us print B. If we print B, we should get what B is. Okay, so now we see it's the answer 1, 2, 3. Now we can see the shape is a 3 comma. Why? We just see it's just 3 columns, so 3 comma. That's just basically it. It has no rows, and again, it's still of a type integer. Now again, a 2D vector or a 2D tensor. Sorry, a 2D tensor is just a matrix. So a 2D tensor. Again, C is this TF constant 1, 2. We see it in brackets, 3, 4. Now let us print C. If we print C, we'll get this. This is what we get. Can you all see the screen? Can you all see the Google Colab I'm using?
Yes.
All right. So this is basically a 2D tensor. So 1, 2, then the bracket, 3, 4. Again, you can see the shape 2, 2 or 2 by 2. And again, it's still a type of 32. So now if you want to just get the shape, you can just say dot shape. So if we do this, we get the shape. A 2, 2. So this is what I'm trying to say. Then the third one is this, a 3D tensor. Okay. A 3D tensor. Then apart from getting the shape, we can also get the data type. By that I just mean the integer. So if I say print C dot D type, again we got an int 32. What we got the other time, an integer. Int means integer. Then 32 is just the number of bits it is stored in. So 32 bits is 4 bytes. So it's just an int 32. That's how we get 32. Then we also have zeros. So if I'm working with zeros or identity matrix, for example, now when we say tf.zeros, remember our tf is TensorFlow. Zeros, it means that the values are going to be zeros. Then the 2 is going to be the row, the 3 is going to be the column. So if I say print z, what will I get? I'll get zeros of what? 2 rows and 3 columns. So that's what we did. 2 rows and 3 columns. The shape is 2, 3, and the data type is what? Is a float. Now a float is just a decimal. Then 32 again. 32 still indicates the memory storage. 32 bits. That's a 4 byte. So it's a 0 point. Again, we see the point. The point. This point here indicates that it's decimal. So a float is just basically a decimal. Then again, if you want to create ones, let me see. If you want to create ones, we can say, sorry, ones is equal to tf.ones. Then again, we specify the shape. We can say a 3 by 3. So print, okay, this will give us an error. Is this? Okay. So we can say print ones. And again, we get a 1. A float type of 33, 3 by 3. So we can change this to 3 by 4. And if we run this, what do we get? We get a 3 row and 4 columns. Now, if we add, let's say, 2, for example, what are we going to get? Now, this is a 3D tensor. So this 3 here, this first number, the 3 here, it indicates the role. So again, when you look at this role, see the 3, 1, 2, 3. There are 3 ones here. This 4 indicates the columns. So 1, 2, 3, 4. Then this 2 here indicates the depth. The depth. That's 1, 2. So if I change this to something like, let's say 5, we should see this. This 3 indicates the role 1, 2, 3. This 4, the columns 1, 2, 3, 4. Then this 5, the depth 1, 2, 3, 4, 5. So these are how 3D matrices or 3D tensors work. So let me give another example. So if I say tf.random, so it's just going to generate random numbers. Then if I say dot normal, it's going to generate random numbers in a normal distribution. So let me show you what a normal distribution is. Let me Google a normal distribution for you. Okay. So if you've ever seen a graph like this or an image like this is basically a normal distribution. So majority of it is located towards the center. So now let us run this. Let us see what we get. Okay, we have to print it out. So print R. So what do we get? Notice that all of these values are close to 0. This is minus 0.2, it's close to 0. This is 0.24, close to 0. Minus 0.5, close to 0. 0.69, close to 0. So that's just basically what the normal distribution is. Now everything is close. All the values are going to be close to the center, and the center is going to be 0 because of the mean is going to be 0. So therefore, all the values are going to be close to 0. Now let's go into those basic arithmetics of it. Basic arithmetic of tensors. So now we have a constant. X is what? 1,2. Then y is what? 3,4. Such that when we add them, what do we get? We get 4,6. And this shape. Why? 1 plus 3 is what? Is 4. Then 2 plus 4 is what? Is 6. So that when you add these tensors together, the 1 and 3 are added together, that's 4. Then the 2 and 4 are added together, that is 6. So let's also try multiplication. So let's multiply it. Let's change this from addition to multiplication. Let's see what we'll get. So 1 times 3 is what? Is 3. 2 times 4 is what? Is 8. So that when we multiply it, we get this value. So again, this was basic arithmetics of tensors. Now, when we're in secondary school, when we did matrices, this was not basically how we multiplied matrices. There was a way we multiplied matrices, and there's a way to do that here. And this is it. So the word or the value is matmul. So again, we have a constant A. A is what? 1,2, 3,4. Then B is what? 5,6, then 7,8. Such that when we multiply it, what do we get? We get 19 and 19, 22, 43, and 50. And basically, this is how matrix multiplication works. So let's say you have the matrix 1, 2, 3, 4 in brackets, and you have 5, 6, 7, 8. So what you do is this: you take this 1, 2 and multiply by 5, 7. Then you take this 3, 4 and multiply it by what? 7, 8. That's how matrix multiplication works. So 1 times you take this 1 to multiply by 5, 7, 1 to multiply by 6, 8, 3, 4 multiply by 5, 7, 3, 4 multiply by 6, 8. So example is 1 times 5 is what? Is 5. 2 times 7 is what? 14. 14 plus 5 is what? Is 19. That's 19. 1 times 6 is what? 6. 2 times 8 is what? 24. 24 plus 6 is what? Is 30. That's here. 3 times 5 is what? 15. 4 times 7 is what? 28. 15 plus 28 is what? 43. So we write 43 here. 3 times 6 is what? 18. 4 times 8 is what? 32. 18 plus 32 is what? Is 50. So you get your final answer. So you get 19, 30, 43, 50. So basically, this is how matrix multiplication works. So let's do this example. Okay, I think that's basically what we did. That's basically what we did. So that's how matrix multiplications work. And so when you get 19, 22, 43, 50, that's how it works. So apart from that, we can also reshape a matrix and reshape a tensor. I don't know why I'm using the word matrix. Reshape a tensor. And this is how you reshape it. So you have a tensor of 1, 2, 3, 4. Now, again, it has 4 elements inside. We want to make the row 2 and the column 2. So that when we print reshaped, what do we get here? We get 1, 2, then comma 3, 4. Now, imagine if we add 5 to this. What are we going to get? We're going to get an error. We should get an error. Exactly. We should get an error. Invalid argument error. The reason being is this. When you have 2, 2 matrix, the maximum elements that can be inside is 4. But now we have 5 inside. So we're going to get an error. So if we add something like, let's say 6, and we make this 2, 3, we know 2 times 3 is 6. And so we should not get an error. We should get 1, 2, 3, then 4, 5, 6. Now, if we do something like comma 1, we should not still get an error. Why? Because of 2 times 3 times 1 is still 6. But now, if we make it something like 2 here, we should get an error because 2 times 3 is 6, 6 times 2 is 12. Meanwhile, we only have 6 elements inside. We should get an error. But let's say we make it 7, 8, 9, 10, 11, then 12. We should not get an error. Okay. It should work just fine. So basically, this is how you reshape a tensor. So you have it just in a 1D here, and we're making it into a 3D. So let me just make this a 2,6 and run it. So basically, this is it, 2,6. Then there's something as indexing. So let me copy this again. Let me paste it there. Let me paste it here. Now, if I want to get the index, let me say print. If I want to get C, then let's say I say this 0. What do I get? I get 1, 2. Now, if I say, for example, 1, what do I get? 3, 4. If I say, okay, let me just explain how it goes. In programming, generally, how we start counting is from 0. So this 1 here is 0. This 2 here is 1. This 3 here is 2. In terms of numbering, that's how we start counting. So we don't start counting from 1. We start counting from 0. So if I want to get 1, 2, I'll click 0. I'll type in 0 rather. If I want to get, let's say this reaches up to 12. So if I want to get the 11th one, or like, again, it's going to pass an argument because of it's meant to take in 2. It's meant to return 2, but 2 so 10. Okay. What's the? Why am I getting error? Okay. So let me just listen. When you want to, so I want to take an element. I want to take 1, 2, 3. There are 12 elements inside, 1 to 12. Now, there's something as slicing. Basically, what it is this. I get if I put this, I should get all the elements. Okay, 1, 2, 3, 4. I'm coming. Let me use a better example. Let me use this. Let me use this as a better example. An experiment. Okay, I know I'm getting an error. I'm putting C instead of T. I knew why. No wonder I was getting the error. Okay, exactly. No wonder I was getting the error. It meant to be T, not C. Okay, I figured out what was wrong. So this is it. The 0 here is going to get the first number, and the 1 here is going to get number 2. Remember, I told you that in Python we start counting from 0. So the the value here 1, its numbering is 0. The value here 2, its numbering is 1. The value here 3, its numbering is 2. The value here 4, its numbering is 3. So if I want to get let's say the 11th one, the 11th one would actually be number 12. So what? I get the value 12. If I put in, let's say 13, I should get an error. Again, error. If I put in anything above 11, I should get an error. If I put 10, I'll get the 11th value. So that's what 11 here. And so basically that's how it works. And I can also, if I put this inside, now what this semicolon is, or this column, means that I'll get all the values. So now if I put, let's say 0, or let's say if I put 3 here, it means I'll get all the values from the third index. So this is 0, 1. So remember that this 1 again is 0. This 2 is 1. This 3 is 2. So I'll start counting from 4. So I'll get 4 to the last one. Now, if I put, let's say, from this 2 to this, I should get 1, 2, 3. So this column means that you start counting from the beginning. Then I'll stop at the third index. So this is 0, 1, 2. Again, I'll not get the third one. I'll stop at it. So I'll get 0, 1, 2. That's 1, 2, 3. And that's how it works. Let's look for other examples. Let's look for other examples. Again, there's something known as concatenation. So concatenation. Oh, okay. This is it. So we see that A is equal to 1, 2. B is what? 3, 4. Now, if I want to make this into a single tensor, but I don't want to add them up, I use the word concat. Now, I specify the axis is 0. And let me show you what I'm saying. When you look at this A, you see that it's a 2D tensor. And this B is a 2D tensor. So I can show something like 1 and comma. Sorry. Let me say here 1, 2. Then comma here. Should I let me say 5, 2, then let's say 3, 7, then here, then comma. Okay, so when we look at this, what this does, what concat does is this: it joins all the matrices together. So you see that this is 5, 2, 1, 7, 3, 7, and 3, 4. That's basically what it does. Now concat joins all the tensors together, so that they form into one tensor of a shape of 4 by 2. Remember, this is a 2 by 2, 2 by 2 again. So it has joined to a shape of what? Of 4 by 2. That's what concat does. It joins tensors along a dimension. Then we can also stack a tensor. So what I mean by stack a tensor is this. If I run this, look at what we've done. We've done 5, 2, 1, 2, 3, 7, 3, 4. So instead of it becoming 4, 2, we've made it into a 3D tensor. That's 2, 2, 2. That's what stack a tensor is. So to stack something means to place something on top. So we've created a third dimension, then we just placed it on top. That's 2, 2, 2. That's basically what to stack means. So if I stack something, I add on top it. Okay. Then this is just the last one I'll take before we go into building our model. We can reduce sum. So if I stack this, if I do this, what would I get? I'll get 5, sorry, it's meant to be reduce sum, not this. Okay. So to reduce sum is this: you add all the tensors, add all the values in the tensors together. So 1 plus 2 is 3, 3 plus 3 is 6. So if I say 4, I should get 10. I should get 10. And basically that's what I get. And this is just basic tensors arithmetics. So if you understand how to work with tensors, from there you can graduate to working with computer vision. And that brings us to what we want to build today. So basically today what we're going to build is that we're going to build a malaria detection model. So we give it an image or we give it a cell. Before I move further, can you guys still hear me? Can you still hear me? Can everybody still hear me? I just want to make sure I've not lost anyone. All right. Thank you. Before I It's this. So when you go to the clinic or the hospital and they want to test for malaria, what they do is that they take a blood sample, they put it or they smear it on a glass, then they take it through a microscope. Then, if it has they look at the cell. If they detect the presence of malaria or the presence of, I forgot the name of the infection. I've forgotten it has skipped my mind. But if they detect the presence, they know that you have malaria. If they don't, they know that you don't have malaria. And so basically, that's what we're going to be doing for computer vision today. We would get the images. When we get the images, we would train the model to be able to detect if an individual has malaria or not, or if a cell is infected or not. And so this is something you can just follow along along with. So we're not going to create a new file. So new notebook in Drive. So if you have Google Colab, okay, Google Colab is free, so anybody can anybody can follow along, and it's something I do advise you to do to follow along and join. Sorry. Okay, so basically, let's name it. Let's say what's this? Let's say malaria detection computer vision. Let's just give it that name. Computer vision. Okay. Okay. Let's say masterclass. Masterclass. Okay. So that's just the name. Then you go to this runtime. Then you click on change runtime type. So for you either see a CPU or H100 GPU. I think these are the two versions you'll see. But there's a paid version. That's the one I'm using. That's why I have access to all these other ones. So you can click a CPU or H100 GPU. I'll just pick A100 GPU. Then I'll click save. So then you come here, you click connect. Then you wait for it to connect. Okay, sometimes it just happens like that, like it has difficulty connecting. Okay, so it's connected. So when you see it, again, you can see that's connected. You see your RAM, you see your CPU and your GPU, and you see your disk. So you are given access to your RAM. So it's 3.5 gigabytes, 40 gigabytes, and just the rest. Just ignore this. So that's what we are going to do. So the first thing we are going to do is that we're going to import libraries. And one of the libraries we used was TensorFlow. So we're going to import TensorFlow. Then we're going to import it as TF. Then again, where we are getting our data from is from TensorFlow too. So we're going to import it. So we're going to import TensorFlow data sets as TF DS. Okay, and what else again? We're going to import NumPy. Import. If you do not work with all these things before, don't worry. I'll just walk you through it. Import NumPy. Import. We're going to import matplotlib. Okay, matplotlib dot. Okay. So TensorFlow again is what we've worked with. Then TensorFlow dataset is what we use for our datasets. Then NumPy. NumPy is just how to NumPy converts the tensors into matrices for multiplication. Then matplotlib is just to visualize your data. Then we are going to also import some other things. These are the other things we are going to import. Okay. So import IO, import intertools. So I'll just explain where everything is here. Matplotlib is for visualizing your data. After that, you have itertools. So iter is just for the short form of iteration. Then import W and B. W and B is going to be a service we are going to be using. It starts for weight and biases. I'll show you how to go through it. Then from sklearn, we're going to import metrics. So this is just to evaluate ourselves. So the confusion matrix, the ROC curve, and the AUC. AUC stands for area under curve. Then from TensorFlow.keras.layers, import all this. And I'm going to just walk you through it. And so the way we're going to be doing this is we're going to be using something called CNN, or convolutional neural networks. And basically what CNNs are, they are this. What are CNNs? I know I have a website. Okay. Okay. So I'll just let me paste this here. Okay. What CNNs are? Well, let me explain what convolution is. Convolution is very, very, very easy to understand. So now you have, let's say, a matrix 1, 2, 3, 4. You have this as a matrix. And you have something known as a kernel or a filter. And you have a kernel of, let's say, 3, 4. But let's even say 3. Let's ignore the 4. Let's remove the 4. You have a kernel or a filter of 3. So convolution is just simply this. When we say something, a convolution, it's just to take the multiplication and then the addition. So now this is a matrix or a tensor 1, 2, 3, 4. Then you have a kernel or a filter. This is either known as a kernel or a filter. Now the filter takes the multiplication, then the addition. Okay, for better word, let me use 4. So it's going to be explanatory. 3, 4. It takes the multiplication and then the addition. So this is a 3, 4. So what we do is this: we multiply this 3 by 1, then this 4 by 3. So 3 times 1 is what? Is 3. 4 times 3 is what? 12. 12 plus 3 is what? Is 15. So the result is going to be 15. Then we do it again for this 2 and 4. 3 times 2 is what? 3 times 2 is 6. 4 times 4 is what? 16. Then 16 times 6 is what? Is 22. So the answer is what? Is 22. So basically, this is just a convolution. So a convolution is this: you take the summation, you take the multiplication, then you take the addition. Now, and the reason why this works is because of what I explained earlier, that all images are just made up of, all images are just simply numbers. They're just simply tensors. So that if we take the multiplication and the addition, we can play with it. And if you understand that, you can work with tensors. So this website, let's look at this website. Okay. So this is just a CNN explainer. So what's the convolutional neural network? In machine learning, a classifier assigns a class label to a data point. For example, so just ignore this. So basically this, a tensor, I explain what tensor is. A neuron. So it is called a neural network because it copies the brain. So you know the brain is made up of neurons. So that's what it takes after. And so a neuron is just basically a function. So a function, and the way it is represented in equation of a line. So remember when we were in secondary school, we did y is equal to what? Mx plus c. This is what basically a function is. Y is equal to mx plus c. M is the gradient and c is the what? Is the bias. That's basically what it is. That's equation. That's just the function. Then a layer. What's a layer? A layer is simply a collection of neurons. So when you have several neurons that come together to perform similar operations or the same operation, that's basically just a layer. Then again, like I said, a kernel. Then let's move to images. We would understand when we see a visual picture. Basically, this is it. Beautiful. So now, this is the input. So imagine this is a 5 by 5. This is a 5 by 5. Let me make it a 7 by 7. The input is a 7 by 7. The padding is 0. Then the kernel size, I told you it's either called a kernel or a filter. The kernel size is a 2x2. So basically, this is this is the red things that you see, they're the kernels. So when all these things are multiplied, they are added, and we get this. Then you move to the next one. You move by 1. All of them are multiplied again. They are added. You move to the next one. They are all multiplied. They are added. You move to the next one. They are all multiplied. They are added. You move to the next one. You move to the next one. Then you move down here again. This again, they're all multiplied. They are added together. You move to this one. They're all multiplied. They are added together. You move to this one. The next one. All multiplied. They are added together. So that's basically what convolution is that you multiply all the values together. When you're done multiplying them, you add them together. And when you do that, you get the output. And what you notice is this: when you begin to multiply or when you begin to use when you begin to convolve, that's the word, the images, you begin to get a pattern. When you get a pattern, you can begin to say, oh, okay, it follows a particular pattern, therefore we can identify objects. And that's basically it. So again, let me give an example. Let me upload a picture of myself. So this is basically a picture of me. Now, if I click on blur, again, this 0, -1, 0, -1, 5, -1, 0, -1, 0, it's a filter. Now, what this filter does is that it sharpens the image. So you notice that at certain places, the image is sharp. Now, if I click on blur, this is a filter. What does it do? It blurs the image. What does it again? If I click on bottom subble, what do you see? It turns it into black and white. If I click on custom retains it to the original. This is a custom. If I click on identity retains the image. So this is how the image looks like. If I click on let's say an outline, what does it do? It outlines all the edges. So again, you see my head shape, you see the tie, you see the collar, you see the shoulders. Again, that's what outline does. The background, again, there is no corner to it, or there is no edge to it, so it's dark, and it outlines all the edges. That's just basically what outline does. Then if I click on sharpen sharpens all the images and sharpens the edge, so it makes it come out more. Let me look for another example for you. Let me go to downloads. Let me look at. Okay, this is just a picture of a cat. This is a picture of a cat. What does it do? It sharpens the outline. So if I go to blur, what will you see? It blurs the image. If I go to custom, you see the image. Then if I go to identity, the image remains the same. That's basically it. So if you work with kernels or if you work with filters, you can play around with images. And what you notice that when you begin to play around with those images, they begin to form a particular pattern, such that from that pattern you can begin to identify if an object is let's say a dog or a cat or whatever. And that's what basically CNN does. So CNN, convolutional neural network, what it does is that it makes use of filters or kernels. And when it makes use of filters or kernels, it plays around with it, it tweaks it here and there, and it begins to form a particular pattern. When it forms a particular pattern, it can identify the image. Let me look at the last. Do I have another example? Okay, yes. Let me show you this last one. This one is pretty visual. Are we still together? If you are still together, please just give me a thumbs up. Hello? Hello? Okay. So now this is it. So it says draw your number here. That's how we draw the number 4. What do we notice? We see that this is first the original image. This is first the original image 4. Then we see that several filters or several layers. These are, again, what are layers? Layers are neurons that are put together to perform similar functions. This is a layer here. Several layers come together and they begin to do what? They begin to detect the image. They begin to take out. So a 4 has what? This stroke here. this stroke here, this stroke here. And what does it do? When you see the output, what does the output? What does the output give? It gives 4. So if I change this to, let's say 6, what does it do? First guess 6, second guess 5. Again, so we see that this image or this model is confused or is not fully accurate. So again, it's saying that the first guess is 0, the second guess is 5. So it doesn't get it right for 6. Let's get another example. Let's say 1. So now,
Sorry, Heritage.
Yes.
Yeah, we're supposed to observe like a 5 minutes break.
Right. All right.
Yeah. So maybe when you are done with this example, then
Okay,
we
we'll
can
observe it.
a 5
All right.
minutes
Thank
break.
you. Thank you.
Yeah.
So this is first guess A1, second guess A0. So basically, this is how convolutions work. That there are layers of neurons performing similar functions, and when there are multiple layers, they can all get information. Therefore, you get a result. So basically, this is how convolution works. Convolution is just this: you take the multiplication of numbers together, and when you're done taking the multiplication, you take the addition of the numbers, and then you get your answer. So we can just have a 10 minutes. Oh, okay, let's just give it to how many minutes break? Yeah, no, Lua. Hello.
5 minutes. 5 minutes.
Okay.
Just 5 minutes.
So
Yeah.
let's say by like 1:17 or 1:18, we should be back. Like 1:18. Sorry, 12:18. Why did I say 1:18? 12:18.
Yeah, and while we are observing the break, if you have any questions, you can put them in the chat box. So when we are back from break, we can the questions later on. Yeah. Hi, hello everyone. So yes, the session is recorded. I can see someone asking. Akunle, yeah, the session is recorded and you'll get the recording after the class. So you can just check out on your emails. You get it via email. Um, so there is a feedback form, the chat. I just sent in a feedback form in the chat. So please fill the form. We would like to know how we can do better, and we also want to hear what your experience has been so far. It's a very quick one. It won't take up to 5 minutes or a minute. So please kindly fill the form. Thank you. And don't forget to drop us in the chat so Heritage can attend to your questions. Okay, so it's 12:18 already. We can continue with the class.
Okay, welcome back. So we just to recap what we did just but before the break. I explained what tensors are. I showed us examples. I explained what convolution is and how basically it works. It's just multiplication and addition. I showed us an example or some websites that give us examples of it. And in this section, we're just going to be working on a project, and I'm going to be explaining to us what it is doing. So again, just to recap, TensorFlow, what we are working with the library, TensorFlow data sets, the data sets that we're going to use for the to train the model. NumPy converts tensors to arrays. Matplotlib just to visualize the data. IO, input output, itertools just to iterate it. W and B, weights and biases. It's a software and it's a company. They provide us certain services. I'll show you how to use it during this class. Then metrics. Metrics is just to determine the accuracy and the loss. So confusion matrix, ROC curve, and AUC. Then again, this import, this conv just means convolution. This max pool. So when you say max pool, it just means to reduce the data. So if you have a let's say 50 by 50 image and you have a max pool of 2, it just divides that 50 by 2, so it becomes 25 by 25. Then normalization. And so normalization simply just means that you reduce the information. And the way we use you make it from 0 to 1. So if you have for example, if you have 0 and okay, let me use this, let me use yellow. Okay. If you have 0 to 255, that's basically how colors work, like I explained earlier. And you want to normalize the picture. So let's say you have 36. What you just do is that you divide it by 255. So any number you divide by 255 is always going to come within the range of 0 to 1. So if I divide 0 by 255, I get 0. If I divide 255 by 255, I get 1. So basically, I just reduce the image or I compress it to 0 to 1. And the reason why we do that is because of machine learning models work better when they are compressed from 0 to 1. So if the values are very high, they don't work so well. Flatten just means this. You have an image, let's say a 3 by 3 image. When we use flatten, it just compresses everything down into just one long array. So when we are going on in the class, I'll just explain. So when we imported all these things, we just run it. Okay, and let me document properly. So we can say imports. Okay, let's say imports. Let's make it bold. This way. So now we have all our imports. When you do that, you run it. Then when we are done with imports, we can just okay. Then the second thing we will do is this: we would load the data. So again, we would load the data, and to do that, this is it. We have data sets, then data set info. So info just means information. Then remember that we have the TensorFlow data set, and we imported it as TFDS. So that's basically what TFDS means. Then dot load, it means we are loading data. Then what we are loading is in malaria data. So when we say with info, it means does it come with the information? If we say true, it means it comes with the information. If I say as supervised, what basically as supervised means is this: we have the image, then we have the value or the output of the image. So let's say we have an image of a cell. Is the cell infected or uninfected? If we say as supervised, it means it comes with the information if it is infected or uninfected. But if we say false, it means that it doesn't come with that. Then when we say shuffle files, it means that should we shuffle the file? That's basically what it means. Then when we say split, it means that we are getting just the trained data. So when we load this, you should download it. I don't know why it's taking this much. Let me reload it. You have not to take this much. Okay. Let me reload this again. Oh, okay. It's working now. So it's basically just downloading the data. Then what we're doing at the end, we're going to say print data set. So we're going to see the data set. Then we're going to say, let's remove this. So we're going to print the data set. It's still downloading and it's extracting right now. It's extracting the data set. For this, let's name it what? What should we name it? Let's say load data set. Let's make it bold. Let's capitalize it. So we have all the imports here. We have the load data set. And it might take some time to load. The reason why it's taking time to load is because of about I think 28,000 or 27,000 files or images it is downloading. So it's taking some time to extract it. Okay. will be done. The advantage is that when you download it once, it just stays there. You don't need to download it again multiple times. So it's almost done. So it's done. So let me, if I reload this, it's on download. This is just what it prints. It prints the data sets, and this is just the data set. So it's a tensor spec. Then the shape, the none means that it's not specified. So the role is not specified. The column is not specified. But the depth again is 3. So I told you that it's an RGB image. That's red, green, blue. That's why it's 3. The data type is what? An unsigned integer. The U stands for unsigned, then the integer, then of 8 bits. Then the name again, it has no name. Then the tensor spec, this is just the output. Again, the output is what? An integer of 64 bits. That's what? 8 bytes. Then when we get that, what we do is this. When you are working with machine learning models, you have generally speaking, the data is divided into 3. You have the data for testing, you have the data for training, and you have the data for validation. And that's basically what it is. Data for training. So you have to train your model. You train your model with a particular data. You have to validate your model, and you also have to test your model. And so we already have the data already. So if I just show you the description, if I show you the info, so I'm gonna show you the info, and then comment this out. Okay. So this is the information. So what do we see? We see that number of examples. We see this 27,558. So the number of images there, 27,558. So out of this 27,558, we are going to break it down such that some of them are for training, some of them are for validation, and some of them are for testing. So the way we'll do it is that we'll break it down in a, let's say, 60, 20, 20% ratio. So we'll use 60% of them for training. We would use 20% of it for validation. Then we would use 20% of it for testing. So let's just comment the code. It's just good to comment, it's just good coding practice. So we can say split data sets. Let's make this bold. Okay. So split data sets. And we'll just create a function to split. So we create a function. This def in its definition splits. We're not creating this function. Then what this function accepts, it accepts a data set. So that's the data set to pass into it. Then it accepts the train ratio. So if we break it down in 60, 20, 20, so 60%, 20%, 20%, is going to accept those 3. Then we're going to find the length of the data size. So if we find the length, we can begin to take 60% of that total length. So normally we know that the length is 27,558. But this is just good practice because imagine if we don't know the length of that data set. That's why I'm going to get the length. I know the length is 27,558. So is this train underscore data sets is going to be this data set, the data set that we receive, dot take. Then we're going to multiply the length of that data set by the ratio. So if we multiply 60%, that's 0.6 of the total length. That means we get 60% of it. Then we'll do the same thing for validation. We're going to take the validation ratio and multiply it by the data set. So we'll get 20%. And we're going to take the test data set and multiply what? The train ratio, 20%. 20% times what? Times the data set. So basically, this is how it works. Then we're going to return the what? The train data set, the validation data set, and the test data set. So let us run this. Okay, we see that it worked well. So the next one again is just, for example, to visualize our data. Let's visualize our data. Let's just say visualize data. Okay. Let's make this bold and let's visualize our data. And we want to, so we have images. Let's just see how it looks. So we can say to see them, we'll just look through it. So we say for I, comma, image, then label. So we have an image, we have a label, then in enumerate Then let's say train underscore data sets. We'll take let's take 20. So we're going to view 20 images. So we're going to just say let's say AX is equal to PLT again. Okay, it already shows us this. Remember that we imported PLT matplotlib, and I said matplotlib is to visualize the data. So that if we run it there, what do we get? We get this. So we get 1. When you see 0, 0 shows that it has it is infected. When you see 1, it is uninfected. So this is just basically how the data looks like. This is just basically the cells. This is how the cell looks like. So this is just to visualize data. Then one of the things we should know again is this. When you are working with computer vision, all your images have to be the same size. So one image cannot be, let's say, 30 by 30, another one by 50 by 50. All of them have to be the same size. So because of that, we're going to make all of them the same size. And we're going to call it resizing or pre-processing. Let's do this. Text. Let's say pre-processing data. So if we pre-process all the data, we're going to resize all of them. So to resize it is not so difficult. This is just it. We're just calling the function resize and rescale. Remind you, I told you. Remember that I told you that to do this thing, to work with computer vision, you have to make your values 0 to 1. So that's why we're dividing by 255. Whatever your value is, you divide by 255. So it squeezes it into 0, 1. So this, let's just let's say let's create this function here. Let's say, or this variable rather. Let's say IM size is equal to 128. So the image is going to be 128 by 128. So let's just make this here. I remove this. Okay, 128 by 128. If we run it, it should work. Okay, it should work. Then we're going to loop through the train data, the validation data, and the test data. So we're going to make everything what the same size. And to do that, we are just going to loop through it. Okay. So now, this train data, we're going to loop through it. Then this, let me just explain what this means. The train data that we have here, we're going to loop through it. So we're going to resize everything. So when we say resize underscore rescale, we are calling this function here. When we say num underscore parallel underscore calls, this is it. When you are working on your laptop, you have several CPUs that are operating. Now, this num underscore parallel, when you see auto tune, it means that the computer is going to decide how many CPUs are going to operate. So if I call like 3, normally it's going to be like 3 CPUs. But if, let's say, 5 or 6 CPUs or core processors are available, it's the computer that will decide. So it is auto tune. It is left for the computer. This shuffle, we're going to shuffle it. Then this batch. So when you're training your image, how many images are you going to be training? When you're training your model, rather, how many models are you going to be training at an instance? So let's say this batch is going to be 32. Batch underscore size. Usually, okay, 32. Usually it's always in a multiple of 8. So it's usually 8, 16, 32, 64, 128. So we're just going to make our own 32. So how many images are you going to train your model on at once? So I'm only going to do 32 images at once. So if we run this, okay, it should go. Then the next one is this. We are going to build the model. And to build the model is not something difficult. So let's just label it. So build model. Okay. We're going to build the model. And the thing we're going to say is this. We're going to say model is equal to, again, a variable. Then tf dot keras dot sequential. So what this basically means is this. When something is sequential, it means it follows, it is turn by turn. So that's just basically what it means. It means after this, do this, after this, do this. So when I say something is sequential, that's basically what it is. It follows, it operates turn by turn. So the first thing is this: we're going to give it an input layer. So input layer, the input layer means the image, the size that the model is going to receive. Again, remember that the IM size here is what? Is 128. So it means that the size that this model is going to receive is what? Is 128 by 128 by 3. That's one. The second thing is this: we're going to pass in a convolution. Now, when we say conv 2D, it's just basically a convolution. Then it's going to operate on 16. This 16 here means the filters. So like the 16 filters. Then this 3 here, I can say, let me say, filters is equal to 16. Then I can say kernel. The kernel size here is what? Is 32. Sorry, the kernel size here is 3. Then that's an activation of ReLU. And so what a ReLU activation means is this: if you have a value, any value that is less than 0, it is automatically 0. But greater than that, it is the value. So if you have 32, if you have 32 as the input, your output is going to be 32. But if you have minus 32 as the input, your output is going to be 0. That's basically what a ReLU does. So for every value that is less than 0, your output is going to be 0. But if the output is not less than 0, your output is going to be that input value. Then now I told you that when you say pool, what we are doing is that we are reducing the size of the image. So now this is a 128 by 128 image. When we pass in a max of 2D, a max pool, we are going to reduce it by 2. So 128 divided by 2 is what? Is 64. So the new value is going to be 64. So this 64 is going to enter here again, this second convolution. When we pass it again, when we do 64 divided by 2, we're going to get 32. So that's just basically how it works. Let me just post here. This is it. So again, it has an input layer that shows the size. Let's say this is going to be 16. Let's make it a variable. Let me see. Filter underscore 1 is equal to, let's say, 16. And filter underscore 2 is equal to 6. So, okay. Then this flatten, what this flatten again? So let me just walk you through it. Filter underscore 1, filter underscore 2. Okay, it's meant to be S. Okay. What this flatten does is this: you have a grid of an image. You have, let's say, you have 1, 2, 3, 4. What this flatten does, it just makes it 1, 2, 3, 4. It just makes everything into just this. This is just what flatten does. It flattens everything out, and it makes it into this. So what we call flatten, this is what we mean. Okay. Then this dense, what this dense layer does is this: it connects all these layers to a neuron. So let's say dense underscore 1. I said, let's make this 128. 128 and dense underscore 2. Let's make this 64. Before I move further, I want to ask, do we understand to this point? Can you all hear me? If you don't understand, can you just please indicate? If you understand, indicate. If you don't understand, also indicate. Lost you guys. If you understand, please indicate. Just indicate through a thumbs up. If you don't understand, also indicate through me a thumbs up. Okay, someone said I'm a little bit too fast. Okay, so I'll try to reduce my speed. Someone said I'm a little bit too fast. I'm sorry about that. The reason is that I'm just trying to make sure we we finish on time. So let me just take this one again, slower. This flatten, what it does is that it compresses everything into just one DRE. Then this dent, it connects the previous layers to it. Then an activation of ReLU. So a ReLU function is this. If the value is less than 0, the output is 0. But if it is greater than 0, then the output is the input. And I give an example. If the input is 32, the output is going to be 32. If the input is minus 32, the output is going to be 0. Then this sigmoid function, what it does is that it returns a value between 0 to 1. That's what it does. Then this dense, the reason why we have a 1 is this. The output is going to be a 1. Either the person has malaria or the person doesn't have malaria. So that's why this dense, this 1 is indicated here. And let's move to the next one because of time. And I also try to be to reduce the pace at which I'm going. So now we've built the model, and we have to compile the model now. So let's compile the model. This is to compile the model. Now we're going to use metrics. Let's make this a learning rate. Okay. So now, this matrix is this. We have true positives, false positives, true negatives, false negatives. What simply means is this. True positive is this. And let me give an example. Is the pen on the table? If the answer is yes, the pen is on the table, and the machine detects that the pen is on the table, is true and is positive. That's a true positive. False positive. Is the pen on the table? No. But does the machine detect that the pen is on the table? Yes. So the positive there is false. True negative. Is the pen on the table? No. Does the machine detect that the pen is on the table? No. That's true negative. False negative. Is the pen on the table? Yes. Does the machine detect that the pen is on the table? No. And so basically, when we apply it into malaria detection, is this. Do you have malaria? Yes. Does the machine detect that the individual has malaria? Yes. Do you have malaria? No. Does the machine detect that you don't have malaria? Yes. Do you have malaria? No. Does the machine think you have malaria? Yes. That's the false positive. Now, the most dangerous one is this false negative. Do you have malaria? Yes. Does the machine think you don't have malaria? No. So that's the most dangerous one, this false negative. Then this binary accuracy. Binary simply means 2. The reason why we're using a binary accuracy simply means this. Is that you have malaria or you don't have malaria. Therefore, the accuracy can either be one or the other. That's why it's a binary accuracy. Then precision and recall is just to get those are just metrics to evaluate how accurate the machine is. Then AUC means area under curve. Then again, this is just to compile the model. If we run it, it should. Okay, let's run this first. Okay, it should work. Then model.compile. Okay, if we run this now, it should work. Okay, yes. Then we have callbacks. And what callbacks simply means, from the name, callbacks are simply this. If something is happening and I call you, I'm in a sense, I'm interrupting you when I'm doing something. So callbacks are simply functions. A callback is a function that runs when the model is running or when the model is training. And let me explain it to us. Just remove this. You can work with this. So early stopping, like early stopping just means this, to stop early. And we're going to monitor the validation loss. This is it. If the validation loss does not improve after 5, the patience means 5. After 5 trials, if the validation loss does not improve, the model should stop training. Now, this is reduce LR. LR simply means learning rates. And we're going to monitor the validation loss. It means this. If the validation loss reduces at 0.5, in an instance of 3, the patience is 3. If it reduces 3 times, it means that we should change the learning rate. So this one, early stopping, means that you should stop it. This reduced LR simply means that you should change the learning rate. So if we run this, it should work. Then again, we are going to train the model now. We're going to train the model. And this is how we're going to train the model. We're going to apply epochs. So what epochs simply means is this. Epochs is how many times the model is going to look at the data. So if I say an epoch of 20, it means that the model is going to look through the data 20 times. So if I run this now, okay, I'm going to put a comma. It's going to look through it 20 times, and it's going to begin to train our data. So let's just wait for it as it's working. Okay, yes. It's still on the 6th epoch. So it's training data. Now, what we get is this. We see the accuracy. The accuracy here is 0.8. Now, when we see the accuracy here, in this next epoch, it jumps to 93. When we see the next accuracy is 94. The next accuracy 95. This one is 95. And again, you see that the accuracy keeps on increasing. This one is 96. This one is 97 or 0.97, 0.96. The accuracy keeps on increasing because of the more you loop it, the more number of epochs you give it is going to increase in accuracy because it has looked through the data once, it improves on it, looked through the data the next time, it improves on it. So this is what epoch does. And when the validation loss, this is the validation loss here. So, okay. We should get the validation loss. What's the validation loss? Okay. Okay, yes, this is the validation loss. Notice that the validation loss here, look at it, is at 0.7. It drops to 0.16. It increases again to 0.18. Now it drops to 0.14. It increases to 0.15. It drops to what? 0.16. Notice that now 0.18, 0.17, 0.16. And this early stopping function is called why? Because it waited for 5 times and notice that what? When you look through this original one, look at this original one, 0.16, 0.1670, 0.1674. This one is lower than this, so it stops. So the model is now trained. So now I'm going to run the model. We're going to evaluate the model. We're going to evaluate the model. And now let's evaluate the model. Okay, so we're done with that. We're done evaluating the model. Then now let's just look at how it works. Let's visualize it. So this is the model loss. The blue one here indicates the train loss. The orange, the validation loss. The train loss means the training loss. Look at the graph. So the training loss is this. We see that the loss starts at 0.8, and it drops down to what? Roughly about 0.17. Then this one drops completely to around what? That's a 0.09, 0.08. This is the model loss. Then this is the model's accuracy. This is, again, the maximum is 1. So it's at 0.95. This is roughly about, let's say, 0.97. This is roughly about 0.95. So this is how the model looks like. This is how it will. So now we're going to have to test the model. We're going to have to pass training data or testing data rather to the model. and see how it looks like. And to do that, let me just explain to you because of let me show you how it will to be like. So we have this y true. This is the value of the actual data. Then we have this y predicted. Now we're going to look through it for images and labels in test data sets. We're going to predict the image and get the predicted value. We already know the true value because of the true value was in the data when the data came. So from that, we're just going to run this. It should take some time. Okay, I think it's done. Yes, it's done. Then the last one, all we are going to do for this one is this. We are going to see the confusion matrix. So we're going to see the confusion matrix and the ROC. And I'll just explain this, and this is just the end of the model. Our model is done. Let us run this. Okay. So now, what this means is this. A confusion matrix, it indicates the true positive, the true negative, the false positive, and the false negative. So now, when you look at this point, you see that the blue indicates 2,500, 2,000. So when it is white, it indicates roughly about the range of 500. Now, this one here, this first blue, it indicates the true positive. So the true positive is blue. So it's roughly about 2,500. Now it is white here. This white here indicates the true, the false positive. This second white that the cursor is indicates the true and the false positive. So it's roughly about 500. This third white here, this second white rather, it indicates the false negative. And this blue here, the last blue, indicates the false positive. And so we see that our model has an accuracy of roughly about, let's look at it here. It has an accuracy of roughly about 97%, and it has a validation accuracy of what? Of about 95%, and a training accuracy of about 97%, such that you are almost sure, or you are close to 100% sure that when you run this data to detect malaria, you're going to get an accuracy of 95 to 97%. So that's basically how this works. And let me show you this last example to show that it works. So we're creating a function here, and this function is going to output if it has if it is parasitized or if it is unparasitized. I'm going to look through it. Now, you notice that this first P indicates what the original data says. This second P indicates what this second value indicates what our model predicts. So now the original one shows that it is parasitized, and when our model went straight, it shows that it is parasitized. This second one, it shows that it is unparasitized, and when our model went straight, unparasitized. So that when we see everything here, we see that everything here is correct. So we see that our model in the first 16 values, it got everything right. So basically, this is just it. This is just a simple machine learning and computer vision project, such that you can detect malaria in a human cell. So we're just done with this. We're done with the class. We're done with this. I'll just leave it up to the organizers if they have any other thing to say or add more. I would also leave the code to this to this project that we've done, I'll just upload the link to the code on my GitHub, and I'll just paste it in the chat so that anybody can see it and get a hold of it. Okay, so that's it.
Hi, Heritage. Is Iyanu on the call?
Ma?
Is Iyanu on the call?
I don't think so. I don't know.
Oh, okay. I was just pulled in. You can close the you can close the webinar. You can close the webinar if you've answered all the questions and that needs to be answered.
All right, I can end the webinar.
Yeah, I mean you can. Are you done? Have you answered all the questions you need to answer?
Is there any question? I don't think there's any question in the chat. If you have any any question, please just paste it. We can do that in the next like 3 minutes.
Okay, all right. Any question? Okay, if there are no questions, please note that the recording or the replay of this session is on YouTube, and
Sure.
you'll receive the replay via email. Thank you
All right,
guys for joining today's session. Enjoy the rest
yes.
of your holidays.